a set. We define a set as a collection of could be a collection or enumeration or a list of distinct objects. There are so many examples we could give. For example, the empty set. We define a set to contain maybe cat, dog, mouse. That could be a set. Then the second question was to define cardinality of a set. I think so. Cardinality. If you remember keenly, we define cardinality as the number of elements. The number of elements of a set. So these objects in your collection, we refer to them as elements. So just count the number of elements and that gives you cardinality. And in this case, cardinality of the empty set is 0 because the empty set does not contain any object. Cardinality, this set A that I've defined, just count the number of elements, 1, 2, 3. It's 3. Maybe if I gave an example, the set of natural numbers, that's also a set, then cardinality of the set of natural numbers would be infinity. So this is an example of an infinite set, even it's a finite set. The empty set is also a finite set because it has 0 elements. The third part of the question, you are given some sets and you are asked to perform some set operations. I don't know what the set A was. Who can remind us what the set A was? I don't have the question.
1, 2. Set A 1, 2. Set B 1, 3.
1, 3. Okay. So I might not be go in order, but A union B. We define union as the collection of all elements that are in either of the set. So they could be in A or in B or in both. So to find union, just put everybody together. So this will be 1, 2, 3. And some of you, even if you write this as 1, 2, 1, 3, it's still okay. Because we're only interested in distinct elements. And so the cardinality, the number of elements in the union, will be 3. So if you want to set to be of this form when counting, just remember to count the element 1 once. And then intersection, A intersect B. So intersection is simply all those elements belong to both sets at the same time. So if you want intersection of A and B, the elements in the intersection must belong to set A and they must belong to set B at the same time. So in this case, the element 1 is in set A and it is in B, so it's in the intersection. The element 2 is in A but is not in B, so it's not in the intersection. 3 is in B but not in A, so not in the intersection. So we have the intersection having only one element, a singleton set. Therefore, the cardinality of A intersect B is 1. And then set difference A minus B. These are elements which belong to A but do not belong to B. So in this case, the element 1 belongs to A and belongs to B, so it will not be this difference. The element 2 belongs to A but does not belong to B, so 2 is in that set. And then B minus A, now we start from B, elements which are in B but not in A. So 1 is in B but is in A, 3 is in B, not in A, so this will contain 3. Then the next set operation is symmetric difference. which we gave 3 ways to find. Yes.
Excuse me. So in the question, it also asks to find the cardinality of each
Yes.
of these problems. So you end up and say the cardinality is.
Yes, you must say that. So cardinality of A minus B is 1. Cardinality of B minus A is 1. I think I've been doing that all through. I've done that for the union, the intersection, and one of the difference that was missing. We define the symmetric difference as the elements which belong to the union but are not in the intersection. Or you can define this as the elements which belong to A minus B put together with the elements which belong to B minus A. So using the first definition, we have A union B, 1, 2, 3, and A intersect B as 1. So what the set difference elements to the union but are not in the intersection. So we take 2, 3. We take 2 over 3. And if you use this second definition, A minus B is a singleton 2, B minus A is a singleton 3. The union of that, just put them together, is also 2, 3. And the cardinality of this symmetric difference is only 2 elements. Is there any other set operation that you were asked to compute?
Yes.
Which one?
Cartesian product.
Cartesian product. Great. Cartesian product. Cartesian product. So you asked to compute Cartesian product of A and B. And so in this case, your elements will exist as ordered pairs, okay? So the first, you take the first element of A, which is 1, and pair it with the first element of B, 1. Then take the first element of A, pair it with the second element of B, so 1, 3.
So you can't see what you're writing.
Excuse me, you can see the board.
Okay, let me write. Are you able to see up here?
Yes.
Okay, so A cross B, A times B. I was just saying that these elements will exist as ordered pairs. So the first pair will be from A, the second coordinate will be from B. So the first element of this guy will be 1, which is the first set. You pair it with 1 in the second set. Then the next element, this one paired with 3. So that is 1, 3. Then the next element will be 2 paired with 1. Then lastly, we have 2 paired with 3. Of course, cardinality of A cross B is 4. You can just count these elements. Or use the theorem that we gave last time, that cardinality of A cross B is cardinality of A times cardinality of B. In this case, 2 times 2, which gives you 4. Suppose you are asked to find B times A. Then now just reverse. So the order now, you start with the element, your first coordinates will come from B, and your second coordinates will come from A. So in this case, you will have 1, 1, 3, 1, then 1, 2, lastly 3, 2. Again, for the same reasons, cardinality of B cross A is 4. That was very easy. And the next part, you are asked please, if there's a question, you are free to ask. Question 2 was on polynomials. Polynomials. First question was define a polynomial. Find a polynomial. We give the definition. So a polynomial in a variable x any expression of the form p of x c naught plus c1x plus c2x squared all the way to cn xn, where ci belong to the real line and is a positive integer. Okay. So many examples of polynomials that you could think of. For example, all natural numbers are polynomials. So for example, I could give 1 as a polynomial, I could give 1 plus x, give 1 plus 2x cubed, I could give x squared plus 4x plus 9,000. All these are examples of polynomials. And we also did classification. So we classify this as a polynomial, we classify this as a binomial, this is also a binomial, this is a trinomial. And then in terms of order, this is order 0. This is first order, the 1 because the highest exponent is 1. This is third order because the highest order is 3. This is quadratic or second order because the highest order is 2. What was the next part? I guess it was on operations. So you must have been given some polynomials. So you must have been given some polynomials. The first polynomial. Which polynomials were you given to perform operations? Hello?
Yes, P of x squared minus 1.
1 plus?
X squared minus 1.
Mute yourself, please.
What was the second part? The second polynomial?
X minus 1.
X minus.
Why? You say that and people here will choose to start a discussion on Zoom.
And Moidera, please mute.
I mean, it's very easy. So x squared minus 1 plus x minus 1. Just collect like term. So this is x squared plus x minus 2. Subtraction. Also,
Excuse me, do you mind increasing the letter? I can see.
the size, huh?
Yes, I can see.
Okay, x squared minus 1 minus x minus 1. Is that okay now?
It's better. Thank you.
And then we just collect like terms. So x squared minus 1 minus x plus 1. This gives you x squared minus x. Because -1 and 1 are additive inverses. So they will give you the additive identity, which is 0. Then multiplication. So we have x squared minus 1 times x minus 1. We said you take each component of the first term multiplied by each component of the second term and add up like terms, so we take x squared multiplied by x minus 1 multiplied by x minus 1. Of course, this is x cubed minus x squared minus x plus 1. And this is the result. It happens that there are no, you cannot simplify it any further. And then lastly, p divided by q. So this is simply x squared minus 1 divided by x minus 1. Now that you've done factorization, you can just factor the numerator and divide, or you could do long division. So x squared minus 1 divided by x minus 1. So how many times does x go into x squared? That's x times. Then take x and multiply this expression. So x times x is x squared. X times -1 is negative x. When you subtract, this becomes x minus 1. So because x squared minus x squared is 0, this will be -1 minus x. So this will become plus and then minus 1. And then x minus 1 go there once. So you have your answers x plus 1. So the quotient of dividing p and q is x plus 1. That was all from the first assignment.
Excuse me.
Yes.
Question part B for the polynomial for px plus qx. The answer is x squared plus x minus 2. Or
The first part, addition.
yeah, since x squared plus x will give you x cubed.
No.
Or
You cannot add x squared and x because x squared is quadratic and x is linear. X squared plus x is just x squared plus x. This is not multiplication. I don't know whether you get me. X squared plus x is not the same as x squared times x. This will just stay x squared plus x minus 2. Remember, x squared has exponent 2, x has exponent 1, so you cannot add two terms with different exponents. Is it clear?
yeah,
So I have a question.
Yes.
So for subtraction, must you put them in brackets so that you can open in brackets? So that you can open the brackets.
Yes. Especially the term that you are subtracting. Especially the term you are subtracting. You must.
So can't you do like x squared minus 1 minus x minus 1?
So you want x squared minus 1 minus x minus 1, like that?
Yeah.
No, this is not right, because this will give you x squared minus x minus 2, which is not the right thing. All these operations must follow Bodmer's, the order of operations. So this bracket is very important, this second bracket, because you're subtracting everything in this bracket. When you're subtracting, when you have p of x minus q of x, you're subtracting all the terms in q from the terms in p. That is why you need to put this bracket and open it up.
Even for addition.
For addition is not that, it doesn't bring any difference. For addition, it doesn't bring any difference. For subtraction, it brings a difference because of this, there's this -1. Remember, you can write p of x minus q of x as p of x plus -1 times q of x. So this -1 is supposed to multiply every term in q. Then you can do your addition. Fair enough.
Yes.
Any more questions?
Sir,
Sir,
could you
can you
please
give an
go through
example?
how number problem 3? I didn't quite understand.
What was problem 3?
It was classifying the numbers as integers, rational,
Oh,
irrational.
sorry, I forgot.
And then,
It's another problem.
no.
So what are the numbers you're supposed to classify?
Those 2, pi, I think the E for indices and logs.
What is
3 minus
2 and then e?
pi.
Pi, okay. Pi.
Yeah. 3 minus 4i. -7. 2/9. Yeah, that's it.
Yeah, and I said that you should list all the cases that apply. Okay. So for example, 2 is a real number. 2 is a real number. It's an integer. It's a natural number. Any other category that fits 2?
Rational.
It's a rational number. How about E? Because it's a real number. It is irrational. Okay. Same to pi. Pi is real. Same time irrational. This guy is complex. It's a complex number. So remember, complex numbers, as you shall see later, they have 2 parts. There is the real part. This is called real part. This is called imaginary part, where this I squared is simply 1. We will look at complex numbers very soon. And then -7, this is real number. It's an integer. It's a rational number. Okay, you can write -7 as 7 divided by -1, or -7 divided by 1. This is a real number. It's also a rational number.
Excuse me, sir.
Yes, go ahead.
What was the definition of a rational number again?
Definition of a rational number. Good. So the set of rational numbers, we define this set as any numbers of the form A divided by B, where the GCD of A and B is 1, the LCM of A and B is 1, and we want B to be non-zero. A belongs to the integers, and B belongs to the natural numbers. So essentially, all numbers which can be written as fractions are rational numbers. Okay, and that includes all the integers and all the natural numbers. For example, give me a natural number like 5. I can write 5 as 5 divided by 1, or I can write it as -5 divided by -1, or I could write it as 10 divided by 2. There are infinitely many ways of writing 5 as a fraction. So all natural numbers and all integers are also rational numbers. And I remember I gave you the order of inclusion. So you have natural numbers contained in the integers, which is contained in the rationals, which is contained in the real numbers. This, as we shall see later, will be contained in the complex numbers. Then we also have that the irrationals is contained in the real numbers. So every natural number is an integer. Every integer is a rational number. Every rational number is a real number. Every irrational number is a real number. And as we shall see later, all these real numbers, we can express them as complex numbers because they're just complex numbers whose imaginary part is 0, but that is yet to come.
Excuse me, sir.
Yes.
It's okay if you, like for me, I wrote the symbols, the ones that you've just written. That's fine, right?
Yeah, that's fine. That's fine. So, yeah.
Okay, thank you.
Sir, in that case, isn't pi a rational number?
Pi?
Yeah, because you can express it as 22/7.
Any suggestion? Anyone with a suggestion on that?
Let me answer.
Go ahead.
Pi is not a rational number since the more you express it, like pi doesn't have an ending. It's 3.142 and then it continues like the Isa said. Like it goes billions. So yeah, it's not.
Okay, thank you.
There is this book by James Cantwell. I don't know whether you guys have read it. It's on symmetries. And in that book, he says that a circle is probably the most beautiful or elementary shape, which you expect to be, of course, it is symmetrical. This is the circle. And it's symmetric about the diameter in the sense that if I divide this into two areas, A1 and A2, these two have the same area. I can reflect the bottom part and I get the top part. So that's what we call symmetry. But the moment you find the ratio, of the circumference divided by the diameter, then you get an irrational number. And he goes ahead and says that symmetry is elusive. It lies because you're dividing a rational number with another rational number and you end up getting an irrational number. So pi is irrational. Remember 22/7, you've also seen in some cases, I don't know, it's normally 3 and 1/7. In some cases, 3.14. Some books 3.142, some books 3.141592653. All these are just approximations. These are approximations. They are not the real value of pi. The real value of pi is not known because after the decimal, it continues infinitely. And there is no pattern. So there is no pattern. You cannot write this as a recurring decimal because all recurring decimals can be expressed as rational numbers. You can write them as fractions. But for the case of pi, there is no pattern. And this number has been studied for by so many mathematicians. Up to now, we have more than 13 billion digits after this decimal point. So pi is a rational number.
Excuse me?
Yes.
In the text, it says -7 is also a complex number.
Yes, -7 is a complex number. After doing complex numbers, you realize that all real numbers are complex numbers because a complex number is simply any number of the form a plus ib, where a and b are real numbers, and I squared is -1. So the square root of -1 is defined as I, or in some books, J. Engineers like to write this imaginary unit as J. And So for example, you could write -7 as -7 plus 0 I, because 0 times any number is 0. So it's a complex number in which the imaginary part is 0. So that's perfectly fine. That's okay. Just view the real numbers as complex numbers in which the imaginary part is 0. Hello? Are we good?
Yeah, we are good. So that means all real numbers are complex then, even what you've defined.
Yes, all real numbers are complex numbers, just that the imaginary part is 0. Because the complex number has a real part and an imaginary part. We'll do a presentation of complex numbers. We normally have this real axis and imaginary axis. So on this x-axis, you have real numbers, and then on this vertical axis, you have all the imaginary numbers. So that if I want to represent A plus B, this would be A, this would be B, and then somewhere there, A plus IB, because this is the direction of I. So the real part is this guy along the horizontal axis, and then the imaginary part are all the guys in the vertical axis. This is yet to come. We will see how to represent this as polar form, exponential form, how to find roots of these complex numbers, how to add them, how to subtract them, how to multiply them, how to divide them. Yes. Any more questions? Okay. Last time we looked at factorization of expressions. So, and I showed you how to factor expressions using common factors. I showed you how to factor trinomials. Trinomials of the form x squared plus bx plus c, and also the form ax squared plus bx plus c, where a is non-zero. We learned how to do this. Then we learned how to factor difference of squares. Difference of squares. We learned how to factor difference of cubes. We learned how to factor sum of cubes. We also defined perfect squares and how to factor expressions which can be written as perfect squares. These techniques would be very useful when we're looking for solutions to quadratic equations. And we also did complete factorization. Complete factorization. So lastly, we were supposed to look at expressions involving, so these are expressions involving fractional exponents or fractional indices. This is the only bit that remained, and I'll give an example quickly. So this is called factoring expressions with fractional exponents. So these are expressions whose powers are fractions. For example, let's say you have 4 x to the 5/2.
Excuse me, I can't see what you've written, sorry.
8.
Factoring expressions with, I don't know, from there.
With fractional exponents, This is fractional exponents. And I'll give you an example, maybe x to the 3/2 plus, I don't know, maybe 8x ½ For example, factorize this expression. I don't know if it will factor or not. It's an example I've just made up. I've not done it before. So the first step is look at the terms. So we have 4, 12, and 8. Okay. Look for the greatest common factor. What's the greatest common factor of 4, 12, and 8?
4.
Greatest common factor, that's 4. Okay. And then now these terms, x power 5/2, x power 3/2, and x power ½ What is the greatest common factor? Greatest common factor for these expressions?
Is it a half?
A half. Did someone say a half? Hello?
Sir, please repeat.
I'm asking for the greatest common divisor or the greatest common factor of this x power 5/2, x power 3/2, x power ½
X power ½
Half. X power half. Yeah.
GCD here is x power ½ And so now the product of this will be a common factor for this expression. So 4x power ½ should factor your expression. Of course, 4 goes into 4 once. Then how many times does x power ½ go into x power 5/2?
5.
Really?
5.
Are you-
Times.
Are you sure? So this is the trick. Huh? You're looking for some number n such that x to the n times x to the ½ gives you x, should give you x power 5/2. Okay. I want to factor x power 5/2 in terms of x power ½ and x power something, which I do not know. Okay. Using laws of indices, or you could just write x to the n being equal to x 5/2 divided by x power ½ I know we have not done laws of indices, but in case of subtraction, you normally subtract indices. So this should be x power 5/2 minus ½ which should be x power
2.
In that case, n is 2.
2.
So this is x squared. Go ahead. Someone had a question.
Please repeat, sir. I don't understand.
From which part?
From the 4 power ½
Okay.
No, sir, from the beginning, start from the beginning, please. From the beginning.
From here. Factoring expressions.
Yeah.
Yeah, so we want to see how to factor expressions that involve fractional exponents. Well, in this case, I mean the powers of the unknown variables x could be fractions. And the first example we're looking at is this 4x power 5/2 minus 12x power 3/2 plus 8x power ½ We want to factorize this expression. And the first step is to find the greatest common factor of the numbers, which are just the coefficients of these terms, 4, 12, and 8. And the GCD of that is 4. Okay? Remember, you could compute GCD 4, 12, 8, then start with the smallest prime number, 2, 2, that is 6, 4, then 2, 1, 3, 2. There is no any other prime number which can divide all the remaining numbers. So the greatest common factor will be 2 times 2, which is 4, as we found before. Okay? Is that okay?
Yes.
Hello?
Yes.
Yes, it's okay.
Then now we want the GCD of this term. So we have x power 5 over 2, x power 3 over 2, x power a half. And so if we start with x power a half, yes, x power a half. Then ask ourselves, how many times does x power half go into x power 5 over 2? So all you are supposed to do is to divide. Divide x power 5 over 2 by x power a half. There is a law of indices on division. A power m divided by a power n is a power m minus n. Let me give you an example before you can use this law. For example, if someone asks you, what is 3 cubed divided by 3 squared? This is just going to be 3 power 3 minus 2, which is 3 power 1, same as 3. Assuming you did not know about this law of indices, then you just go ahead and compute 3 cubed. Well, that is 3 times 3 times 3 divided by 3 squared, which is 3 times 3. This top part is 27. That's 3 cubed. And then 3 times 3 is 9. Then when you divide 27 by 9, you get 3. Okay? So here we are going to use law of indices to do this division. Just subtract the powers because the base is x. In this case, is the same. So this should be x power 5 over 2 minus a half. I'm just subtracting the exponents. So the exponent in the numerator is a half. 5 halves. Exponent in the numerator is a half. Subtract. What is 5 halves minus a half?
2. 4 over 2, which is 2.
Which is 2. So this should be x squared. So here is squared. Okay.
Excuse me, sir.
Yes.
So how do you get an 2? How do you get 2?
How I get 2?
Yeah.
Yeah, so first of all, are you okay with this subtraction of indices? I know I've not proven this, but trust me, we'll prove it later in the course, but for now, just trust me that it is true. So 5 over 2 minus a half. Well, the LCM is 2, so 2 into 2 ones, 1 times 5 is 5, minus 2 into 2 ones, 1 times 1 is 1, 5 minus 1 is 4, and 4 divided by 2 is 2. Is that okay, Abdiakim?
Yes, sir. Thank you.
Great. Then the next is x power 3 over 2. We do the same. So you want x power 3 over 2 divided by x power a half. And as I said, subtract the exponents. 3 over 2 minus a half. That is going to be x power 1. Okay? 3 halves minus a half is 1. So this is x. And then x power half into x power half, that is just 1. So at this stage, there is no any other common factor in the remaining terms, x squared, x, and 1. So your GCD is just x power a half. And that's why I picked the GCD in this case to be x power a half. So now, common factor in the entire expression will be the product of these two factors. Okay?
Excuse me, sir.
Yes?
Excuse me.
You're excused?
Yeah, could you go over this factoring thing again?
Factoring?
Yes, this x 5 over 4, 3 over 2, 1 x half. Could you go over it again? I didn't get that part.
Which one? This stage?
Yes. Yes, that place.
And you know how we got 4?
Yes, I understood that.
Yes, so we are looking for a common factor in this expression, the same as getting the GCD. GCD of x power 5/2, x power 3/2, and x power half. So our first candidate here is one with the lowest exponent, which is x power half. We will just treat them the same way we did with the numbers, okay? So how many times does x power half go into x power 5/2? You get that by division. The same way in this case, how many times does 2 go into 4? You take 4 divided by 2 to get 2. How many times does 2 go into 12? You take 12 divided by 2 to give you 6. How many times does 2 go into 8? You take 8 divided by 2, giving you 4. So that is the same thing we are doing over here. So for the first part, I will need x power 5/2 divided by x power 3/2. And I've given you a lot of indices. Anytime you're dividing exponents with the same base, just subtract the index of the numerator from the index of, subtract the index of the denominator from the index of the numerator. And in this case, index of the numerator is 5/2, index of the denominator is 1/2. It's 1/2. And this gives you x squared, because 5/2 minus 1/2 is 4/2, and 4/2 is simply 2. So here we get x squared. And then for the second case, how many times will x, the half, divide x to 3/2? It's the same as dividing. So the number of times x power half will divide this will be the same as x power 3/2 divided by x power half. So you compute x power 3/2 divided by x power 1/2. That is going to be x power 3/2 minus 1/2, which is x power 1. Because 3/2 minus 1/2, the LCM is 2. So this is 3 minus 1. So you get 2 divided by 2, which is 1. So you just have x with one exponent. This is x. Then of course, x power half divides itself once. We are computing the GCD, so we stop at this stage because there is no any other common factor in the remaining terms. So we pick this as the common factor, the greatest common factor. So now, the common factor for the entire expression will be the product. So now we need to factor out the product, which is 4 times x power 1/2. Of course, 4 goes out into 4 once. And then x power 1/2 will go into x power 5/2. X squared times, if you remember our table there, 4 goes into 3, in 12 3 times, so we have 3. And of course, x power 1/2 into x power 3/2, you get x power 1. Then plus 4 goes into 8 twice, x power 1/2 divides this once. So that is your first stage of the factorization. And remember, I said, if you want to check that you're correct, just expand this and see if you get back the original expression, okay? Then now check if this part can be factored, because this is a trinomial. And we said, so to factorize this second part, you need 2 terms. Factoring x squared minus 3x plus 2. You need 2 terms whose product is 2 and sum is -3. Okay. So if I take -1, -2, well, I can write -3 as -1 minus 2. What is the sum? Then the product, -1 times -2 is 2. So that means we can write x squared minus 3x plus 2 as x squared minus x minus 2x plus 2. Then now group the terms. So then in the first group, the common factor is x. So we have x into x minus 1 minus the second group, the common factor is 2. So this is 2 into x minus 1. Then here you can factor out x minus 1 because it's common. So we have x minus 1 in the first group, x minus 2 in the second group. So we have factored x squared minus 3x plus 2 as x minus 1 times x minus 2. So finally, we will have that 4x power 5 over 2 minus 12x power 3 halves, like 8x per half will be given by 4x per half into, so instead of x squared minus 3x plus 2, we have x minus 1 times x minus 2. And of course, to check if you're right, just expand the whole expression and see if you get back.
Do we leave the answer as 4x per half, or we have to factorize till the end?
We leave the answer at this stage.
Why did we do this other part?
Which part?
This part for the 3x.
This part.
X squared minus 3x plus 2, yeah, this part. Or it was another question.
No, it's the same question. I was factoring this term. I was factoring this second part. And we found that this factor of x minus 1, x minus 2. So then now, this is my final answer. 4x power half into x minus 1 into x minus 2. Where x minus 1 into x minus 2 is x squared minus 3x plus 2.
Why are we factorizing this other part?
Yeah, we need to factorize it completely because we did factorization of trinomials. That was the first. That was the second technique after common factors. And this is a trinomial, so you must go ahead and factor this. Of course, not all of them will be factorizable, but in this case, we found a trinomial which can be factored. You could find two numbers whose product is 2 and sum is -3 as -1 and -2, because -3 is -1 minus 2, -1 times -2 is 2. So you can factor this expression.
Sir, can you please give another example?
Yes, we can look at another example. So let's say we have 1 plus x, 2/3 x plus 1 plus x
Could you write in a bigger handwriting?
Yes, just a minute. I'm still trying to come up with an example that will work. me see. Well, I don't know if it will work out, but let's see. Okay. So the first has an exponent 2/3. We want to factor 1 plus x 2/3 times 2x plus 1 plus x power negative a third. Okay. It looks scary, but maybe you could start by let y be 1 plus x. Then you could write this as y power 2/3 times 2x plus y power negative a third. Okay. Of course, there is no x, so we cannot factor out x, we cannot factor out 2, but y is common, so of course we can take y power negative a third because it is the smallest exponent. And then so we will have y power negative a third into, so let us ask ourselves, how many times does y power negative a third? Of course, this will be 2x first. How many times does y power negative a third will divide y power 2/3? So that should be y power 2/3 divided by y power negative a third. And with these quotient, same base y, different exponents, just subtract the indices. So 2/3 minus negative
1.
a third, that's 1. Okay. Y plus 1. Okay. So we have, from here we have y power negative third 2xy plus 1. And then our y is 1 plus x. So what we have is 1 plus x power negative a third into 2x 1 plus x plus 1. Okay. I don't think you can proceed any further. Maybe try to open the brackets. Let me see. So this will be 1 plus x power negative a third into 2x plus 2x squared plus 1. Will it be possible to factorize this? Maybe, maybe not. Because if you look for two numbers whose product is 2, two numbers whose product is 2, and sum is 2, I don't know of any two numbers whose product is 2 and sum is 2 at the same time. Because this is like solving the problem xy is 2, x plus y is 2. This will not give you any rational numbers, so just leave your answer at this stage.
Sir,
Yes.
I have a question. Can you please repeat this question, this example?
Yeah, we can repeat the example. That's not a problem. So we want to factorize. We want to factorize 1 plus x 2/3 times 2x plus 1 plus x power negative a third. Then I started by letting y to be 1 plus x. So where there is 1 plus x, I replace with y. Then the expression becomes y power 2/3 times 2x plus y power negative a third. And then because we have y as a base in each of the terms, I pick the y with the smallest exponent. The smallest exponent in this case is negative a third, because negative a third is clearly less than 2/3. So then anything power negative a third must be dividing something power 2/3. So then I factor out y power negative a third here. In the first term, so we'll have 2x, and then now what should come next is y power 2/3 divided by y power negative a third. And by the law of indices that I gave you, this means you subtract the exponent, so this should be y power 2/3 minus negative a third. 2/3 minus negative a third is the same as 2/3 plus a third, which is the same as 1, because you will have 3 divided by 3. So you get a y, and then you divide the whole term as 1. So we are having y power negative a third times 2xy plus 1. And then now you just bring back our y. Remember, y was 1 plus x. So where there is y, we replace with 1 plus x. And then we expand the last term like that. You don't have to make this substitution. It's not mandatory. I just did it to simplify, to make the expression look simple. But it's not mandatory that you make this substitution. You can just work it out without this substitution.
Excuse me.
Yes.
Do we leave the answer as it is, or can we order the according to the degree?
We can order it according to the degree, but you could also try to see if this can be factorized. Huh?
Excuse me, sir.
Yes.
Sorry, but could you please explain how you got to that answer? Just this last part. Yes, please.
From here.
Not from there. From there. Yeah.
From here.
Yeah.
This first part is okay. I just did the expansion. So I have 2x into 1 plus x plus 1. 2x times 1 is 2x. 2x times x is 2x squared. And then last is 1. Someone is insisting that we write this as 2x squared plus 2x plus 1.
Thank you.
Let me see. B squared minus 4ac. This will not have real solutions. So you can only factorize this in the complex field if you have not done.
Sir, I have a question.
This system will not have real solutions. No real solutions. The solutions will be complex. I will show you later how to check if an equation will have real solutions or not.
Sorry, sir, I have a question.
Yes.
Yes, for where you wrote 2x and then you put into bracket 1 plus x. So I'm just wondering, because you put minus 1 over 3 as I understand why you put minus 1 over 3, but like 1 plus x, I think it should have like an exponent of minus 2, or I'm mistaken, because I'm a bit lost there.
This 1 plus x has an exponent.
Yes.
Yes.
But when you factorize it, you factorize actually 1 plus x to the power of 1 or minus 1 over 3, right?
Yes, good. Yes. Yeah.
Then I'm just wondering why, like when you are
why we have this one here.
I'm just saying, like you know the y that you wrote here, the right that you wrote 2xy, that y I think should have an exponent of -2, right? For it to be
okay, that's an exponent of 1.
How?
That's an exponent of 1, which is 2/3 minus a third. This is the same as 2/3 plus a third. This is the same as 3 divided by 3, which is 1. And this other one has an exponent of 0. But why any number raised to 0 is always 1. That's why I wrote this as y power minus a third 2xy plus 1. Because any number raised to 0 is, you can even try this with your calculator. Take any number, maybe 22 million, raise it to 0, you'll get a 1. And then when you write y times y raised to 1 is the same as y.
Okay, thank you.
Any more questions? Any more questions?
So I have a question.
Yes.
-1/3 minus -1 minus. I've got it. Thank you. Numela.
Okay, good. Any more questions?
Sir, can we have like such a question like this in the exam where it leads to no real solution?
In the exam, I will make sure it has real solutions. This is something I have not done. I was just trying to come up with an expression.
Oh, okay.
I will ensure that one has real solutions. I will ensure. So that should not worry. Any more questions? We will look at what we call a discriminant when solving quadratic equations, and I will show you how to use a discriminant to check if a quadratic equation has real solutions or no real solutions. Let us look at what we call rational expressions. Rational expressions. Rational expressions. So in this subject, we will define a fractional expression. We'll define a rational expression and give examples of which expressions can be considered as rational expressions, which one are not considered as rational expressions. We will look at the domain of a rational expression, and then we'll see some algebraic operations on these expressions. How do you add them? How do you subtract them? How do you multiply them? How do you simplify them? How do you work with complex expressions, compound expressions? So first definition. A fractional expression is a quotient of any two algebraic expressions. Any two algebraic expressions, where algebraic expressions in this case will involve unknown variables. So it could be the variable x, y, z, k. For example, an example of a fractional expression, I could just have a fractional expression, maybe 2x plus 6 divided by x squared plus 7. This is a fractional expression. So it's an expression in which the numerator and the denominator are algebraic expressions. So my numerator is an algebraic expression, the variable x. My denominator is also an algebraic expression, the variable x. I could also have maybe 4x plus y raised to maybe 7/6 divided by x plus square root of 7 y. This is also fractional expression. So the numerator is an algebraic expression in x and y, and the denominator is an algebraic expression in x and y. Okay. We also have 2x divided by 7y plus 10. That is also a fractional expression. The numerator is an algebraic expression. The denominator is also an algebraic expression. Okay, so all these are examples of of fractional expressions. Just take any two algebraic expressions and divide them, write them as fractions. You get what we call a fractional expression. Then we have rational expression. Rational expression. Definition. This is a quotient stroke ratio of any two polynomials. Any two polynomials. So you must remember what's a polynomial. Can someone remind us what's a polynomial? What's the definition of polynomial? What's a polynomial? In this definition, we have a polynomial. What is a polynomial?
An expression of form px.
So a polynomial is simply
an expression consisting of variables and coefficients.
Yes, variables and coefficients. The coefficients are real valued, and the exponents have to be positive integers. Okay. So let's see some examples of rational expressions. So we will only consider expressions in which the numerator and the denominator are polynomials. So examples of rational expressions. For example, this first example, 2x plus 6 divided by x squared plus 7. This is a rational expression because the numerator is a polynomial. It's a linear polynomial. The second part is a quadratic polynomial. So this is a rational expression. You could also have x cubed plus 4x minus 6 divided by x power 10 plus x power 7 plus x. This is also a rational expression because the numerator is a polynomial, the denominator is also a polynomial. So two things to remember. A fractional expression, just take any two algebraic expressions and write them as fractions, where the numerator and denominator are all algebraic expressions. Rational expression, you take polynomials and write or divide them or find the ratio of the quotient. So rational expression is a quotient of any two polynomials. The numerator and the denominator must be polynomials. Algebraic expressions, they don't have to be polynomials. For example, this second fractional expression, the numerator is not a polynomial. Can someone tell me why the numerator is not a polynomial?
Because of y raised to power 7/6.
What about it?
It's not an integer.
What is not an integer?
7/6.
7/6 is not an integer. So this is not a polynomial. And even the denominator we are having a square root. We are having a y power half, which is not
an integer.
So in this, we will be dealing with expressions whose which are ratios of polynomials, strictly polynomials. Maybe a small exercise. I'll write an expression and you tell me if it's a rational expression or not. Excuse me. So quickly, are these rational expressions? If yes, why? If not, why?
The first one is not.
Reason?
The exponent of the second x is not an integer.
Yes, so we are having, so this is not a rational expression. Reason being, we have a half of an exponent. Or just say the numerator is not a polynomial. Just say numerator, not polynomial. Numerator is not a polynomial. How about the second one? The second expression, is this a rational expression?
So I can't see what is in front of x. Is it 1 or 5 in the denominator?
It's cosine, cosine, cosine.
Oh.
This is cosine. You guys remember your trigonometry. This is cosine of x.
It is a polynomial.
Sorry? Is this a
It is a
rational?
polynomial. Yeah.
A polynomial.
A rational expression.
Is this a rational expression?
No.
No,
Why?
because the denominator is not a
That's an expression.
Doesn't have any leading coefficient.
Does not have a leading coefficient. The numerator has a leading coefficient, 1. The denominator also has a leading coefficient, 1. Leading coefficient of the highest exponent.
Because of the cosine.
because the cost is not an integer or
Because of the cosine, not an integer.
The cosine is not an integer.
It's not
Well,
supposed to. It's supposed to be a real number. And it ranges between -1 and 1. So
The cosine is irrational.
The cosine is irrational.
it's a real number.
It's not definite. It goes on and on.
The range of the cosine is
-1 to 1.
-1 to 1. And what is this set? This is a set of real numbers. Okay?
Yeah.
So this is actually a real number.
Yes.
That all real numbers are polynomials. Just that they are constant polynomials. So this will be a rational expression. This guy is a polynomial because this will eventually be a real number. This is a real number. So treat this part as constant polynomial. And then the last one is obvious. This is a rational expression. Any more questions? Any more questions? Have you guys understood why this is a polynomial?
Yes.
Yes.
because cosine will take values from -1 to 1, and all these values, for any x or y or any variable you use, you always get values between -1 and 1, which are real numbers. So this is actually a polynomial, because this will eventually be a real number.
And if it was sine or tangent instead, would it still be
If it was sine,
yeah.
if it was sine, yeah, sine is also sine will also give you values from -1 to 1. Okay. And then tangent, you have to be very careful with the tangent, because tangent gives you from -infinity to +infinity. And some of these are not real. So we're only interested in real coefficients. Infinity is not a real number. Okay. So you have to be very careful when dealing with the tangent, because tangent of 90, -90, or 270 will take you outside the real line. You get infinite numbers. The next definition I would like you guys to take home is domain. Domain of a rational expression. In the first class, we defined, well, in the second class, we defined a function. And I gave you the domain of a function and the codomain of a function. So the domain of a rational expression, definition, domain of a rational expression is the set of numbers, the set of real numbers the expression is allowed to take as arguments, or just say the set of real numbers for which the expression makes sense. And in this case, making sense means you're looking for finite values. For example, so I will give you an expression and the domain. We will also compute values for the expression at some point. So for example, let's have an expression defined by 2x plus 6 divided by x squared minus 1. Okay? We want to find the domain of this function. So we want to look for the set of all real numbers, which if you plug into this expression, will give you numbers that make sense. In this case, will give you finite numbers, numbers which are different from infinity. For example, if you put 2 in this expression, what will you get? You get 2 times 2 divided by 2 squared minus 1. This is 10 divided by 3. So it means 2 is in the domain. 2 is in the domain because we get the output is a number. Okay. How about if you put -1? What is f of -1? So just replace x with -1. This is 2 into -1 plus 6 divided by -1 squared minus 1. Well, that is just -2 plus 6 divided by 1 minus 1, which is 4 divided by 0. What is 4 divided by 0?
Infinity. No, infinity.
So that tells you
So I have a question. So if you divide 10 by 3, it is recurring. So it is finite or infinite.
There's no problem. It is recurring, but it's a finite number. It's a finite number in the sense that if you draw the real line, the real number line, 0, it will be, so this is 1, 2, 3, 4. 10 divided by 3 is somewhere between 3 and 4, right? It's going to be 3.333 going on forever. But we are sure it's a number between 3 and 4. So it's a finite number because it's in between this. We know 4 is a real number, 3 is a real number. So any number in between this is also a real number. So it's finite. It's okay if it's recurring as long as it's a finite number. There's no problem. You can always bound two finite numbers. Yeah. Abdi Hakim, did I?
Yes, sir. Yes.
Okay.
So you didn't answer the question for divided by 0.
Yes. What is 4 divided by 0?
Infinity, I think.
Infinity.
0.
4 divided by 0 is 0.
It's not 0. It's 0 divided by 4. That's 0. 4 divided by 0 is infinity.
So that simply tells us that -1 cannot be taken in by this argument, okay? So we are looking for all real numbers for which we will not have a division by 0. This will be the domain of this rational expression. So before we find this domain, let me give you a remark. The domain of a rational expression P of x divided by Q of x is the set of all real numbers except where Q of x is 0, because so you do not want this denominator to be 0. So anytime the denominator is 0, that number will not be in the domain. So if you wanted the domain of this expression, remember we cannot try all real numbers, they're infinitely many. So straight away, let x squared minus 1 be 0, because we know all other real numbers, it will be okay, except when this denominator becomes 0. So right away, equate it to 0, and then work out the value of x. You can factorize this difference of squares. So this is the same as x squared minus 1 squared, which is the same as x minus 1 times x plus 1 being 0. And from your high school algebra, remember that this means x minus 1 is 0, or x plus 1 is 0. Therefore, x is 1, or x is -1. So this expression that we gave here, the denominator will be 0 at 1 and -1. Now you will write that the domain of f of x is the set of all real numbers. You take away the numbers in which the denominator is 0, so the set of 1 and -1. That will be the domain. So any other real number you put here, this expression will make sense. You get a finite number, except 1 and -1. So in the whole real line, just delete the points 1 and -1. That will be the domain of this expression. Remember this remark, we are taking all real numbers except those real numbers for which the denominator is 0. Okay? Let me give another example. Let me give another example. Your x and the domains of these expressions. Those two will be enough. Very quickly, what's the domain of the first expression?
All the real number except the singleton 2.
Yes, so the domain of G, the set of all real numbers, you remove 2. Okay. How did you get 2?
X minus 2 is equals to 0.
0, therefore X is.
Yeah.
Great. How about the second part? So this is done. Second part.
Excuse me, sir, I have a question.
Go ahead.
So you said the domain of G is all real numbers except 2 or until 2?
Except 2.
Okay.
All real numbers except 2, because if you put 2, you'll get 4 divided by 0. But for all other real numbers different from 2, you'll get finite values. How about h of x?
All the real number except 2 and 1.
Why?
If you call x squared minus 2x plus 2 equals to 0, you'll find 2 and 1 as possible answers of x. I don't know if I made a mistake, but that's what I found.
Yeah.
Okay, so you are right. So you could actually factorize this. We have done this before. This is x minus 1 into x minus 2. This expression will be 0 at 1 and 2. So the domain of h of x will be the set of all real numbers except 1 and 2. So that is how we compute the domain of a rational expression. And even in general, the domain of a function will be the set of all numbers with the function is defined or makes sense. It's not infinity. Okay. Next, we have simplification. Simplification of rational expressions. How much time do we have?
3 minutes.
3 minutes.
3 minutes. 3 minutes will not be enough for this. So let us stop there. Next time we will look at simplification of rational expressions.